I'm excited to be here and talk about some of the exciting demonstrations that have been done on the Honeywell trapped ion quantum computer. So today I'm joined by Wojciech Burkott from BEIT and Jules Tilly from atRahko, and we'll be talking about some of the different demonstrations that have been run on the Honeywell machine. So the Honeywell quantum computer is based on trapped atomic ions. In specific, our qubit is stored in two hyperfine states in the ytterbium-171 ion. And these qubits, these ions are levitated above a microfabricated chip trap that's manufactured and designed in-house at Honeywell. So we can rearrange the qubits at will in what's called the QCCD architecture. And having mobile qubits that can be rearranged has several very nice advantages. The first is that we naturally get all-to-all connectivity. If you want to do a gate between a qubit on one end of the chain, rather than having to do a series of logic to get the information from one side to the other, we simply rearrange the chain and move the two qubits next to each other and do the gate. This also gives us very high fidelity gates. Whenever a gate is done between two qubits, actually those are the only two qubits in the well where the gate is done. And so this means that our gates are also very scalable. As we add more and more qubits to the device, the interaction that gives us our two-qubit gate remains exactly the same. It's always just those two qubits in a single well while we do our two-qubit gate. And so the fidelity stays the same even as we add more qubits. It also means that we have sort of a native ability to do mid-circuit qubit measurement and qubit reuse. If we want to measure a single qubit, we can just move all the other qubits out of the way, measure that qubit, reinitialize it, and continue on with the circuit without destroying the quantum information stored in the other qubits on the device. And we can actually use the results of that measurement to do a conditional gates later on in the circuit. This is absolutely an essential element if you're going to do any sort of quantum error correction. So everyone needs to develop this eventually, but it's something that we sort of natively have in this QCCD architecture where we can move our qubits around. So today we're going to hear about several examples and that use all of these features. But I'm going to spend the first little bit of time talking primarily about qubit measurement and reuse and how that can be used not just for error correction, but in the NISQ era with limited qubit numbers right now. So to start, I'll give an example with the Bernstein-Vazirani algorithm. Now, if you don't know what this algorithm is, that's okay. It really isn't so important for this example, but there's some quantum circuit shown here on the screen where we're marking this oracle, in this case, 01101. But I've drawn this in a very arbitrary way. If we look at just the very top qubit listed there in the circuit, you'll realize that although we initialized this qubit and did its first single qubit rotation at the very beginning of the circuit, that was entirely unnecessary. That could have waited all the way until right before this two qubit gate with the ancilla, which is our bottom qubit there. Likewise, if we look at the second qubit in the circuit, you'll notice that because it's marking a 0 on that qubit, it doesn't do any two qubit gates at all. It's just initialized, has two single qubit rotations, and then is measured. And we can perform that really at any time during the circuit. And if I go through the entire circuit in this manner, you can see that I've written this in a very suggestive way that shows that actually in this Bernstein-Vazirani algorithm, each one of these qubits acts very independently, where it only ever interacts with the ancilla. And so I can stretch the circuit out like this, and you can see that if I can measure a qubit and then reinitialize it, I can condense the circuit down to run just on two qubits. And so we've done this. We run this on the Honeywell system model H0 machine, both the standard version using six qubits available and this two qubit version, and we see we get the same output. But because we can do now any arbitrary length oracle with just two qubits, just to show off a little bit, we went all the way out to a 100-bit oracle here. Right, so that would normally take 101 qubits to run, but we've done it just in the two because of qubit measurement and reuse. Now, if the Bernstein-Vazirani algorithm in this manner gives you a little bit of heartburn, I don't blame you. It's an oracle algorithm, and it's really not clear what's going on inside that black box of the oracle when I'm doing repeated measurements and reinitialization. So I'm not going to claim any sort of quantum advantage here, anything interesting, but I think it's a very nice way to show how in many circuits, one qubit is done being used before another qubit is even started. And so if you have mid-circuit measurement and reuse, there's a lot of algorithms you can run with less qubits than you might naively expect. So for perhaps a more useful example, let's look at the quantum adder. So here I'm adding two different numbers. In this case, it's the number 3 and the number 1, where on this top sum register, I program in the number, do a quantum Fourier transform, and then do a series of controlled rotations based on the input register, which in this case is the number 1. But of course, before undoing that quantum Fourier transform and reading out my answer, I could add in other numbers if I so wanted. So here I'm adding the number 1 in repeatedly to that circuit. But the problem is that this takes more and more qubits as you have more and more inputs. But just like in this Bernstein-Vazirani algorithm I showed you, you'll notice that that first input register is sort of done doing all its job before the second input register starts to do anything interesting at all. So with qubit measurement and reuse, you can condense this down to run on just the 6 qubits that were available at the time on Honeywell system model H0. Okay, so our friends at Accenture helped us run this algorithm, and they showed that by reusing these qubits, you can avoid having multiple input registers. But they also showed that you could, if you were to run this algorithm in a different fashion where you add the 2 numbers, undo your quantum Fourier transform, and then use that answer as the input, you could run arbitrary number of additions with just these 6 qubits, but it require many extra 2-qubit gates as you're undoing and redoing this quantum Fourier transform over and over again. And so you see a higher success rate because of this partial reset in the middle of the circuit. Here's a different example from our friends at Entropica Labs where they did some quantum machine learning. So in this quantum-born machine, you have some circuit with some variable parameters that gives you some outcome. You compare that outcome to some classical distribution that you want, and then optimize those parameters in your circuits to have the machine learn the distribution that you're after. In this case, they were looking at this 3x3 grid for bars and stripes. So with these 9 qubits, you're looking to identify all the states where it's all vertical or horizontal lines. So just those 14 states out of the 512 possible states you have with these 9 qubits. But at the time, again, we only had 6 qubits, not the 9. So they were able to use those 6 qubits to represent the 9 you would need for this machine learning by measuring some of the qubits in the middle of the circuit and then re-entangling them, essentially trading time for more qubits. And so with these 4 layers of entanglement in the circuit shown below, they were able to do this machine learning problem. And on the right is the data run on our system. So in orange, you have the simulation. So this is what you get if you had a perfect quantum computer where you get 60% overlap with the desired states. And in the blue is the actual data, 48% fidelity. So there's room for improvement both on the performance of the machine and perhaps on the ansatz used to get higher fidelity on the simulation. But I think this is a very appealing demonstration that does more than just moving around our boxes on our lines and looking for when qubits are unused. This is showing that you can do the machine learning algorithm with only having part of the entanglement travel from one half of the circuit to the other. I'll give you one last example from Justin Urka and Id Subashi at University of Texas and Los Alamos National Labs, respectively, where they showed how to do qubit-efficient entanglement spectroscopy. So in entanglement spectroscopy, usually what you're trying to do is you're measuring the trace of powers of your reduced density matrix. And one way to do this is with what's called a 2-copy test, where you make 2 copies of your quantum state, you entangle them with these C0 gates as shown, and then you measure the output. But that's just n equals 1. If you want to get higher orders of this density matrix to get more information about your entanglement entropy, you need more copies of your state to get that additional information. So with n equals 2, you need 4 copies of your quantum state. And with n equals 3, you would now need 6 copies of your quantum state. And it continues to increase as n increases. Now, although it's not immediately obvious just staring at this diagram that some qubits are done with their job before others even start, that is indeed the case. And they were able to show that with just 6 qubits, you can go to arbitrary depth n on this circuit to get all the information you want about your entanglement spectroscopy. So they ran this circuit. Here, there's 3 different lines for 3 different values of theta, so different amounts of entanglement in the 2-qubit state they were probing here. And you see that our experimental data with the dashed line there. But I think what's more impressive than the match between the ideal and the experimental is the fact that they're able to go out all the way to n equals 7. Right? So n equals 7 would typically take 28 qubits to do, but here just on the 6 qubits, they're able to measure this entanglement spectroscopy. Now, I don't have any time to go into it, but there is a talk on Thursday from Mike Fossweg, also from Honeywell, showing how you can also simulate large quantum systems using small numbers of qubits by, again, using mid-circuit measurement and qubit reuse. So with that, I want to turn some time over to Wojciech Burkott from BEIT, who's going to be talking about some of the experiments they've run on the Honeywell system.
Thank you very much, Brian. And also thank you very much for the opportunity to test our ideas, especially around the mid-circuit measurement in the actual algorithms and their implementations on the real hardware. All right, so we were obsessed with unstructured search algorithm as it seemed to be the easiest one, showing in the larger number of qubits actual quantum advantage. Quadratic only, but still better than none. So we tried to not only think about how to build that efficiently, but also how to demonstrate that in the actual hardware. We started with the previous implementations on superconducting qubit machines, and up until very recently, the best you could do to show any advantage over the classical solution was all of 3 qubits, 3-qubit search, 8 states, 1 marked, and you are about to find this one state with a probability better than what you could achieve classically. We were able to run up to 6-qubit search on the Honeywell machine, but it started trying to benchmark against the superconducting qubits, where our results for 4-qubit search were very close to the classical number, classical probability of success for unstructured search. The features implemented in Honeywell allowed us to do tremendous progress. First off, the fidelity of the gates allowed us to make sure that we are actually getting some results. Also, mid-circuit measurement and full connectivity allowed us to reduce the number of CX gates, the basic 2-qubit gates, when implementing larger gates necessary for this computation. And last but not least, mid-circuit measurement allowed us to have an implementation of the CCX gate, which on average uses just 4.2 CX gates. Again, thanks to mid-circuit measurement and the reliability of the recovering the state after the measurement. So reset is also important for us. And actually, Brian mentioned the conditional execution of the circuit. Depending on the measurement result, yes, we had that, we tried this, and it actually works. So the results. As I said before, we did experiments on the superconducting qubits. We managed to get the 4-qubit search, almost as good as the classical one, 24.5% of the result. And 3-qubit search was done before, and we repeated those results. It was prior art. So here are the results. As you can see, we run different algorithms. You can judge this by the different shapes of the wireframes depicting the theoretical values. And after repeated runs and many series of runs, we got the black dots. And for the expected result, we also have the error bars from which at this time mark the span between the best and worst of our results. And middle picture shows the mid-circuit measurement for used to enhance the result. Summarizing, you'll get something which is truly remarkable. This is 5 different implementations of the unstructured search for 5 qubits. As you can see, all those algorithms perform better than the classical counterparts. I think it's first ever demonstration of the actual quantum hardware performing the unstructured search, having some advantage over the classical implementation. That's 6-qubit search. As you can imagine, we had the H0, system model H0, so the 6-qubit was all we could do. But with those results, I'm trusting that you can actually have even bigger searches. As you can notice, there is some glitch at the pattern, which is different by just 1 qubit. And that was something which we were able to rectify. We, thanks to Honeywell, we had 2 sessions. And we rectified the glitch of the first one, providing almost real-time feedback on the actual measured results to our friends at Honeywell. And the second run, after several weeks, proved successful. So with that, I can assure you that the Honeywell machine, especially thanks to the mid-circuit measurement, which was my obsession for many years, as Brian rightly noted, necessary for any error correction. So also helping in getting stuff more efficient if you can implement that in the actual hardware, that were our results. With this, I'll pass to Jules, who will talk about yet different brand of the experiments on the Honeywell machine. Thank you very much.
Thanks a lot, Wojtek, and thanks a lot, Brian, and the Honeywell team for inviting me to share the results that we got on the HS0 system. So I'll start my presentation now, and we're going to talk about implementing a computation of molecular excited states on Honeywell's system. So at atRahko, we focus on finding new methods of using quantum computers to solve quantum chemistry problems. And in particular, we're looking at methods in which quantum chemistry fails in general. One good example of this is molecular excited states. So classical quantum chemistry usually fails at getting good, accurate results for these states. All the computing requirements for it tend to be way too large to be fully implemented. And as a result of that, quantum computing places itself as a technology that could really unlock a lot of potential for quantum chemistry and computation of molecular excited states. And we're thinking about fields like drug discovery, or another important application is, for example, making efficient batteries. So in order to do that, at atRahko, we've developed a method which is focused on obviously computing molecular excited states, but that can run on current quantum computers. It's a method which is inspired from the machine learning research, and more specifically, what we call the generative networks. So I'm going to give you a brief description, and then we'll move on to the results. So in order to implement this method, we need 3 quantum circuits. The first one is a quantum that can produce a model of our molecular ground state. So you can obtain this doing, for example, the variational quantum eigensolver. The second circuit is very similar, that at the moment it produces a random state. We don't know what it produces, and it doesn't really matter for now. The third circuit is tasked to take either of these two as input and try to distinguish between the two. Now, following the rules of quantum mechanics, it can only perfectly distinguish between the two if these two states that are produced by the first circuits are orthogonal to each other. Their overlap is 0. That means that if we do that and we train all this circuit together, and at the same time we try to minimize the energy of the state produced, we can obtain the first excited states of the molecule. So it's very convenient because it runs on computers several times now. And what we wanted to do with Honeywell is to really try to push this method to its limit. And the main benefits of Honeywell's HS0 system for us was the outstanding gate fidelities. In addition, because of the full connectivity, we were able to prove our quantum circuits as well in order to make it more efficient. So we run 2 experiments on 2-qubit and 4-qubit molecules, and I've presented on this slide the results that we've. As you can see, we've reached outstanding accuracies on all of the results we've obtained. So on the left, you have the 2-qubit molecule. On the right, you have the 4-qubit molecule. For those of you that have more of a background in quantum chemistry, the 2-qubit molecules are both within 1 millihartry of the result, which means that we are within accuracy. And on the 4-qubit molecule, the first result, the ground state, is within 1 millihartry, while the first excited state is within 10 millihartry, which is still an excellent result considering the technology. So what we can say is that this produces a very promising future of quantum computing, and in particular, the future of application of quantum chemistry in quantum computing. And that closes my presentation.